Good day, distinguished attendees. I'm honored to present our work titled Deep Learning for Climate Change and Natural Disasters, Trends and Applications. My name is Astra Mikail, and I collaborate with Arya Prianto and Telematics from Universitas and UIN Sunan Gunung Jati, Bandung. In this presentation, I will walk you through the rationales, method, and insight gathered from our systematic study on how deep learning supports environmental and resilience. The presentation consists of 5 key parts. We begin with an introduction, followed by the motivation and problem statement. Then I will describe the methodology used in our iterative review and taxonomy construction. This is followed by our analysis and comparison of deep learning methods across climate change and disaster domains. I will then conclude with future results and directions and wrap up with the key takeaways. Climate change and natural disasters are increasingly affecting both ecosystem and human society. Traditional methods often fail to capture the nonlinear and spatiotemporal nature of environmental data. In contrast, deep learning enables automatic hierarchical representations and data sources such as satellite imagery, sensor streams, and even social media. This capability positions deep learning as a crucial tool improving environmental predictions and real-time response. Although many studies have applied deep learning to environmental challenges, we notice significant fragmentation. Most works benchmark models in installations like generalizability across geographies and rarely consider explainability or multimodal function. With goals for structures statistics, our goal is to analyze how various deep learning models perform across tasks, what trade-off exists in terms of accuracy and speed, and how future systems can be designed more effectively. The implementation of deep learning in this domain is not without hurdles. First, data scarcity and class imbalance limit performance in under-monitored areas. Second, the diversity of the data types from satellite images to seismic signals to textual information challenge model for integrations. And the third, interpretability remains a critical concern. High-stakes situations. Moreover, most models require substantial computational resources, which poses limitations for deployment in vulnerable or low resource. And this is our methodology that we use during this iterative review. We conduct a systematic review of studies published between 2022. 20 and 20 and 25. Using academic database such as ICWT and Science Direct. We applied Boolean search technique to filter relevant works. We assessed them based about progression, quality, relevance, and citation index. From this process, we built taxonomy that connects deep learning methods with their data types, use cases, strengths, and limitations. Our review revealed that several deep learning models are frequently used depending on the nature of the task. CNN or convolutional neural networks are by far the most commonly adopted, particularly for spatial data processing. The models are highly effective in classifying satellite or aerial image for tasks such as flood detections, fire recognitions, and greenhouse gas estimations. The reliability of deep learning system heavily depends on the quality and structures of datasets. In climate modeling, the most dominant dataset is ERA5, provided by the Copernicus Climate Change Service. It offers hourly global reanalysis data with fine spatial resolutions. And for the ERA is often long-term trend analysis and forecasting. For disasters, applications is MDAT is a global disaster database that documents occurrence of natural and man-made disasters since 2009. It is constructed 1900, sorry. It is structured and includes metadata such as event type, severity, geographic isolations, and human impact. Our analysis synthesizes quantitation outcomes across multiple studies to evaluate performance metrics of deep learning models. For instance, CNN-based fault detection by generally achieves 797 accuracy, demonstrating in strength in spatial classifications. Another CNN application in extreme weather detections achieved 19%, validating in early warning system. And for the LSTM, have shown diverse performance. Research by Chaturvedi used LSTM to downscale regional temperature data with a mean absolute error of 1.2 value. In contrast, LSTM application in wind-based disaster predictions achieve up to 98 accuracy. Okay, for the next slide, this is our comparative study. Several insights emerged that we can show that CNNs excel in spatial analysis due to their convolutional operations, but they lack temporal memory. They are ideal for tasks like image classification or segmentations. On the other hand, LSTM can handle long-range dependencies in time series data, making them better and suitable for climate forecasting and trend modeling. But they often requires more computational time and are sensitive to sequence length. Okay, to conclude, deep learning continues to revolutionize environmental predictions and response. It improves accuracy, speeds up decision making, and enables adaptive disaster monitoring. However, limitations such as data security, limit interpretability, and high inference latency need to be addressed. Matching model designed to specific task demands is critical for maximizing impact, especially in real-world deployments. Okay, this is for the future works. Future efforts should be prioritize, explainability through SHAP or attention visualization, and leverage hybrid models combining CNNs with LSTMs or transformers. Multimodal fusion using satellite, sensor, and textual data must be further explored to address the security and privacy federate and self-supervised learning and are promising. And moreover, enabling real-time inference via edge computing and formatting open well annotated dataset will make deep learning solutions more inclusive and scalable. Thank you for your attention. We trust that the insight presentation will support further understanding and development in the field of deep learning for environmental challenges. Thank you.